Step 2, calculations. Now that you've successfully generated your hypotheses as well as designed data tables, it's time to fill those data tables in and collect your data through calculations using Hardy-Weinberg equations, okay? So for step 2, you are going to complete the Hardy-Weinberg calculations procedure outlined on Canvas. And make sure that as you're working, you're recording your data and your calculations in that lab notebook in those data tables that we made, okay? So starting with the first part of step 2, we're going to calculate the allele frequency for each allele in this population using our observed values that we were provided back earlier on in this case study, okay? So keep in mind though, we are trying to calculate allele frequencies here. The information that you were provided previously were the number of individuals with each phenotype and ergo genotype, right? So RR, for example, is a genotype, but R by itself is the allele, okay? So we're trying to calculate the frequencies of each allele. So just the frequency of R and the frequency of Y, right? And so we can use this, or we can do this through our Hardy-Weinberg equation of P plus Q equals 1, remembering that the frequency of the R allele is going to be represented by P, and we're using Q to represent the frequency of our Y allele. So just like with any frequency, you are going to calculate each respective frequency by dividing the part over the whole. What does that mean? That means that if you're looking at your population, you're provided with information on the number of individuals with each genotype. For example, looking at the R allele, you are going to look at the number of R alleles in your population, the total number of R alleles in your observed population, and then you're going to divide that by the total number of all alleles in your population to get you that frequency of the R allele. Make sense? Okay, so that's part 1 of this step. You're going to calculate your allele frequencies for each allele, R and Y, in this population. The next step is you're going to use the allele frequencies that you just calculated to then calculate the expected genotypic frequency for each genotype in this population. You're going to do this using the first Hardy-Weinberg equation of P squared plus 2PQ plus Q squared equals 1. Remembering that P squared represents our genotypic frequency of RR homozygous organisms, 2PQ represents our genotypic frequency of the RY heterozygous organisms in our population, and Q squared represents the genotypic frequency of YY homozygous organisms in our population. So to do this, you're going to plug in the P and Q values that you just generated, right? The allele frequencies that you generated in that previous step into this equation. So for example, to calculate the expected genotypic frequency of RR homozygous organisms, you would take the allele frequency of the R allele, or represented by the letter P, and square it, right? P squared. These are your expected values, because these are the numbers we would expect to see if the population is in equilibrium. The next step is you're going to multiply the expected genotypic frequency by the number of organisms in the actual observed population. And this will get you the expected number of organisms in the population if the population was at equilibrium. And then you're going to go back and double check that you have already recorded the number of organisms in your actual population with each genotype. These are your observed values, because these are the numbers of each genotype that you actually observed in the population, all right? This is in stark contrast to the expected number of organisms, which we calculated using our expected genotypic frequencies. Make sense? Now, because we are using our Hardy-Weinberg equilibrium equations, not only are we able to discern whether or not our population is likely evolving or at equilibrium, we can also use these equations to check our work to make sure that we are following each step properly. So what you can do is take that Q value that you calculated and your P value that you calculated, and if you add them together, they should always equal a sum of 1. And the same goes for the other equation of P squared plus 2PQ plus Q squared equals 1. If you find that the sum of these two equations is equaling 1, then you know that you have carried out your calculations correctly. And if they do not equal 1, that means we should backtrack and redo our calculations again.